All right, so this is the second lesson on evaluating limits, really just looking at a few special cases compared to the last lesson. Starting off with an expression here or a function that involves absolute value. When dealing with absolute value, it's very useful to rewrite an equation in absolute value in piecewise form, and that's really thinking about what these absolute value brackets are doing to x minus 3. So let me write this in piecewise form. And so f of x equals one of two pieces. I also might as well factor the numerator. So the numerator of x minus 3 times x plus 3. Now let's think about what this absolute value in the denominator is doing. If x minus 3, whatever that is, okay, not the absolute value part, if x minus 3 is greater than 0, then these brackets are doing nothing. Right? If x minus 3, if all that together is positive, then these brackets are doing nothing. And so one of my pieces will be just like this. But that's if x minus 3, like I said, is greater than 0. All right? Now I would say if it's greater than or equal to, but that's it. If all of this is equal to 0, then notice I'm dividing by 0. So again, if x minus 3, not x, if x minus 3 is greater than 0, then these brackets are doing nothing. The other piece, the other case, doesn't affect the numerator. But if x minus 3 is less than 0, then these absolute value brackets are just changing the sign. And so algebraically, I can show changing the sign as multiplying by -1, or just putting a negative in the front. And so notice I can cancel out a factor of x minus 3 here or here. So let me clean this up a bit. And so this ends up being the same as either x plus 3 over 1. So in fact, I'll just say x plus 3. And that's when x minus 3 is greater than 0, or if I add 3 to both sides to this inequality, when x is greater than 3. That's a simpler way of stating that. My other possibilities is if I have x plus 3 all divided by -1, which if I do that, I might as well just realize I'm just changing the signs. So I'm going to rewrite this as negative x minus 3, or minus 3 take away x, all the same thing. And that's when x is less than 3. And again, for each of these, I basically just added 3 to both sides of the inequality. And so what I look at the end here, this is what I really want to work with. This expression here in piecewise form. I have two simple linear functions. If x is greater than 3, I look at the top piece. If x is less than 3, I look at the bottom piece. If x equals 3, I look at neither because I'm dividing by 0. So I know f of x is not defined when x equals 3. It doesn't mean I can't find the limit necessarily, though. And that's what we're looking at here, finding the limit as x approaches 3 from the left, from the right, and from both sides. So from the left of f of x, that's when x is a little less than 3. So when x is less than 3, right, I'm approaching from the left, that means I'm looking at this piece right here. And so this will equal, I can just literally substitute 3 right into the equation, minus 3 take away 3, which is -6. Right, I look at that bottom piece when x is less than 3, and if I'm approaching 3 from the left, these are values less than 3. Infinitely close to 3, but still less, so I look at that bottom piece. So that's -6. All right, as I approach 3 from the right, that means I'm going to look at the top piece, because from the right, x is more than 3. And so it's just going to be, this is going to be equal to 3 plus 3, which is +6. So notice these are not the same, which means I approach from the left and from the right, I approach different values, which means if I ask for the limit as we approach 3, I know this is going to not exist. So it does not exist. And so with absolute value, almost always at some point, if we want to work with it a lot algebraically, we probably want to break it up into its two pieces. And again, absolute value brackets are deceivingly tricky sometimes, but in the end, all they're doing is changing the sign if the entire input of the absolute value is negative. Otherwise, they're just brackets. All right, so let's look at this example. In this case, I have something in piecewise form, but not absolute value. But I have these two pieces here. And again, 3 is a sort of dividing line between. Notice when x, well, I don't want to say too much. So let me first find the limit as x approaches 3. Okay, so as x approaches 3, because notice my function is not defined when x equals 3. So when x approaches 3, I got to look at, okay, what happens as I approach from the left and from the right. So I want to think about two different limits here. I want to think about the limit as x approaches 3 from the left, and separately I want to think about the limit as x approaches 3 from the right. And so as x approaches 3 from the left, that means values of 3 are a little bit less than 3. Sorry, values of x are a little less than 3, so I'm looking at the top piece. And so I can just substitute 3 right into that equation. There's nothing stopping me from substituting 3 into the equation, so 2 times 3 minus 5, that equals 1. Okay. So let me approach 3 from the right, which is values more than 3, which means I look at the bottom equation, the bottom piece. So this will equal 1 over 3 minus 2, because the equation is 1 over x minus 2. And simplify this, I get 1 again. So they're the same, which means now I can answer this question. I can now actually answer what the limit as x approaches 3 is. And so I'll say here, therefore, the limit as x approaches 3 of g of x is equal to 1. All right, so let's look at g at 3. Now, I've actually kind of mentioned the answer to this already. G at 3 means what's the value of g at 3? And again, this is not a limit. And when I look at this function, when x actually equals 3, I look at neither piece. So I have not defined what to do when x is 3. So this is literally undefined. That's it. OK, so now the limit as we approach 2. So first, as we approach 2, again, it's a two-sided limit. So think about the left and the right. Let's look at my equation. And I look at, so when x approaches 2, I'm looking at the top equation. And as x approaches 2, I have a simple linear equation. There's no reason I can't just substitute 2 right into it. And so I should do that. Again, it's never a bad idea to try substituting the limit right into the equation. Just usually doesn't help. In this case, it does. And so I can just substitute 2 right into the equation. And I get 2 times 2 minus 5 is negative 1. All right. So the last thing I want to talk about is something called the Squeeze Theorem, or the Sandwich Theorem, which is actually something it's called. And the idea is finding the limit of something like this, in which if we look at this graph, this kind of weird graph, this is the graph of 5x squared times the sine of 1 over x. And what's kind of hard to tell potentially, but you can definitely see as we approach 0, this wave oscillates more and more and more, more and more and more. And if I had this in Desmos, if I zoomed in, I would still see that same idea of it just oscillating faster and faster and faster. But it does seem to be approaching 0. But I can't tell, because even if I had this in Desmos and I zoomed in, I would just keep seeing more and more faster and faster oscillations. So I want to look at this function here and think, what's the limit as we approach 0? It seems like it's 0, but how can I prove that if it just keeps oscillating more and more? It's always, and the closer we get to 0, the more it oscillates. And when x actually equals 0, I can just see from my expression, it's undefined. Right? When x actually equals 0, I have the sine of 1 divided by 0, which is undefined. And so I can't find the sine of an undefined number. So how can we find the limit of this? You know, like I said, it looks like the limit of this is going to equal 0. Well, the idea is if we can't find the limit of all of this directly, we can find it indirectly by squeezing it between two simpler expressions. What do I mean by that? Well, again, let me start with just the sine part. And so I'm going to start with just the sine of 1 over x. I don't really care what x is. The output of sine of 1 over x is always going to be between negative 1 and 1. That's just knowing the sine function. But it doesn't matter that it's the sine of 1 over x compared to the sine of x. The outputs will never be more than 1 and never be less than negative 1. Right? That's just what we know about the sine function. So what I want to do now, starting with that, is I want to start to kind of take this and logically get closer and closer to this entire expression right here. So I'm starting with the sine of 1 over x. So we know this is always true. Okay, as long as x is not 0, I know this is always true. The outputs will always be between negative 1 and 1. All right, well now I want to multiply everything by 5. And so then I have negative 5 is less than or equal to 5 times the sine of 1 over x, which is less than or equal to positive 5. Okay, that's it. You want to remember when dealing with inequalities. Oh, that's not an inequality. When dealing with inequalities right here, the inequalities will switch signs if you multiply or divide both sides by a negative number. But 5 is a positive number, so I can just leave those as are. Next, I want to multiply both sides by x squared. And make a little note. If x is negative, and again, x is a variable, if x is negative and I multiply both sides by a negative number, these inequalities will switch signs, but it is x squared. And so note that no matter what, x squared will always be greater than or equal to 0. So I don't have to think about what effect it might make if these inequalities have to switch around. So then I get negative 5x squared is less than or equal to 5x squared times the sine of 1 over x, which is less than or equal to 5 times x squared. And again, right here, this is that function that we're trying to find the limit as we approach 0. OK, so I've just done a few steps, kind of working from the inside out. And now the question is, how does this help me? Well, notice what I have here is a statement that I know must always be true. I know that 5x squared times the sine of 1 over x must always be between these two quadratic functions. OK, how does that help me? Well, I can't find the limit of this weird function in the middle directly, 5x squared times the sine of 1 over x. But I can find the limit of the two quadratic functions. And so I'm now actually going to find the limit of all of this at the same time as x approaches 0. The limit as x approaches 0 of minus 5x squared. The limit as x approaches 0 of all of this. And the limit as x approaches 0 of positive 5x squared. So here's the idea. This I can find the limit of quite nicely. The limit as x approaches 0 of negative 5x squared. That's a weird looking 5. Let me make that 5 a little nicer. I guess that's better. Except my x is gone. Come back. There we go. So the limit of negative 5x squared as x approaches 0 is 0. I can visualize the graph of negative 5x squared as a parabola. And as x approaches 0, the vertex is right at 0, 0. Or I can just substitute 0 into x. And you get negative 5 times 0 squared. So either way, I know that equals 0. OK. Let me look at this side. The limit as x approaches 0 of positive 5x squared. Well, that's also going to equal 0. So I get this statement. Like I said, I can't directly evaluate the limit of 5x squared times the sine of 1 over x. Because like I said, it just keeps oscillating more and more. But I have now logically determined that whatever the limit of 5x squared times the sine of 1 over x as x approaches 0, I know it's somewhere between 0 and 0. Well, obviously, then it has to be 0. Therefore, I know the limit as x approaches 0 of 5x squared times the sine of 1 over x must equal 0. Because right here, in essence, I logically found a way to squeeze this weird function, 5x squared times the sine of 1 over x, between two simpler functions. And because the statements above were always true, I know that when I got to this point, when x was shrunk down to 0, I know that, again, this limit must be between 0 and 0. And you can kind of imagine, if you look right here, you kind of imagine two parabolas, one looking something like this, and one looking something like this. One being positive 5x squared, one being negative 5x squared. And this function of 5x squared times the sine of 1 over x being kind of compressed in between them, or I shouldn't say compressed, being squeezed in between them. And so this idea of finding a limit of something I can't find directly, but by imagining it being squeezed between two functions, here's one example of that. Now, to be honest, I'm not going to expect you to come up with things like this on your own right now. I just want to more introduce you to the idea, which I then want to use to prove this last question, which is to prove this limit that I mentioned before I want us to memorize, this really important trigonometric limit. And that's a limit, in this case, of theta as theta approaches 0, of sine theta over theta equals 1. This is something that we actually looked at in an earlier lesson, and we just substituted values close to 0, a little bit less than 0, a little bit more than 0. I said at the time it's a really important limit. I want to algebraically prove it to you using the Squeeze Theorem. Okay, and first I want to start with this visual here. And on this visual, I want us to notice I have theta. I have the sine of theta, right? If you look at this, we have, because from this angle here, the sine of theta must equal opposite, this line in green, over hypotenuse, which is 1. And so dividing by 1 in this case is not necessary, so I know that opposite length in red must be the same as the sine of theta. So that's why that's labeled like that. Okay, so that's the sine of theta. I have this arc length here. or a sector length. That's why it has an S. That's the exact same as theta as long as we're dealing with radians, because we have a radius of 1 right here. And one thing you may recall that the definition of a radian is the angle necessary so that the arc length is the same as the radius. And one thing that it's useful to remember about radians, and maybe you're not aware, is that when we're dealing with radians and we have a radius of 1, then whatever angle you have here is always the exact same as that there. And until now, that's not a terribly useful fact in what we've done so far, especially in pre-calculus 12. But again, anytime you're dealing with radians and you have a radius of 1, the angle is the same as the arc length. And lastly, I want to draw one more line on here, a tangent line. A line tangent at this point going like this. So tangent means it's crossing the circle at 90 degrees, or it's meeting the circle at 90 degrees. The length of that line right there must be the tangent of theta. So how do I know that must be the tangent of theta? Well, let me just call it x for a moment. And notice if I look at this, I have a big right triangle if I want, where the hypotenuse is on the bottom. So from theta, the tangent of theta is going to equal opposite over adjacent, in this case x over 1. Well, the divided by 1 is not nearly necessary, so I can now see that the tangent of theta must be the same as that line x. So I'm just going to call this, instead of x, I'm going to call it the tangent of theta. And really, this is why we call the tangent function a tangent, because a tangent line is a line that meets a curve at some point and perfectly matches the slope at that one point, like we have in this. That's it. In the end, what really matters is I have 3 lines I want us to now pay attention to. This vertical line, the sine of theta, this sector length, which is just theta, and this tangent line, which is the tangent of theta. So I can just see visually by looking at this that the sine of theta must be the shortest of these 3 lengths. The tan of theta must be the longest, and that sector length must be in between. You can just see that visually. This is sort of a geometric and algebraic proof. And so now I can state that. I can just see that it doesn't really matter where this angle is, whether it's up here or down here. I'm always going to have the same fact, that the sine, that vertical line, is always going to be the shortest, the tangent line is going to be the longest, and the sector length is going to be in the middle. And so I can now write it like this. I can say, therefore, I know the sine of theta must be less than or equal to just theta, which must be less than or equal to the tangent of theta. All right. So now I have the setup for my squeeze theorem. That's it. How do I want it? What do I want to do? Eventually, I want to get that middle part the same as sine theta over theta. I'm going to logically approach there. So right now, I know this statement's always true. So the first thing I want to do is divide everything by the sine of theta. And there's always more than one way of approaching this, but if I divide everything by the sine of theta, then I get 1, which is less than or equal to theta over the sine of theta, which is less than or equal to tan theta over sine theta. My writing is extra messy this morning. All right, let me clean up tan theta over sine theta. If I look at, let me highlight this. Okay, if I look at that part right there, note tan theta is the same as sine theta over cos theta, all divided by sine theta. That means I can write this as sine theta over cos theta times 1 over sine theta. So you can see how these sines cancel out. Same as 1 over cos theta. So let me do that. Let me write this as 1 is less than or equal to theta over sine theta, which is less than or equal to 1 over cosine theta. Well, next, if you look at the middle of my expression, I have theta over sine theta. I want it to be sine theta over theta. I want the reciprocal of that, which means I can just find the reciprocal of everything. And just if I do that, I just have to switch my inequality around. And let me kind of show, for example, if I make a little note right here, if I just pick 2 fractions, I know 1/3 and 2/3. It's clearly right now that 2/3 is more than 1/3. If I now write the reciprocals of these, I get 3 over 1 and I get 3 over 2. It's now the other way around. The inequality, and this will always happen. And so I can just write the reciprocal of all these. The reciprocal of 1 is 1. The reciprocal of theta over sine theta is sine theta over theta. And the reciprocal of 1 over cosine theta is just cosine theta. And now I can just switch these around. And now I have this expression in the middle, sine theta over theta, that I wanted to have in the beginning. And so now I can actually evaluate my limit, because if I look at the 1 and the cos theta, I can evaluate those limits separately. So now let's actually evaluate these limits. The limit as theta approaches 0 of 1 must be greater than or equal than the limit as theta approaches 0 of sine theta over theta, which must be less than or equal to the limit as theta approaches 0 of cos theta. All right, so this is nice and easy. The limit of 1 as theta approaches anything is going to be 1. It's just the number 1. That's a nice number. And over here, the limit of cosine as theta approaches 0, well, I can directly substitute. The cosine of 0 is 1. And so we have this again, where I couldn't directly evaluate the limit of sine theta over theta as theta approaches 0, but I can see it's a number between 1 and 1. So therefore, I know, with this sort of geometric and algebraic proof, I know as theta approaches 0 of sine theta over theta, I know it must equal 1. And again, I'm not going to expect you to come up with these proofs on your own. I'm never going to expect you just to regurgitate a proof to me. That's just memorization. I'm just hoping you can see logically this idea kind of makes sense. And really, I think one of the hardest parts was first getting to this step right here, was seeing how this is true. And again, notice it was kind of a visual. I started with the visual here, and then I went to the more algebraic side. Either way, that proof, we never want to forget it. It's a fairly pleasant proof. Sorry, say it again. That limit, we never want to forget it. It's a fairly pleasant limit. The proof, it's up for debate if that's pleasant. And again, this idea will come up again later on, and we'll never have to use it a ton. I more just want to, like I said, introduce the idea to you. But please don't think now that I'm going to expect you to come up with stuff like this on your own. Not in this class. So that's